Guys, Corey here. Just wanted to make a couple videos before I start on a big AI project I was going to make a big video series for. And I want to do two little short videos on some introduction to two basic AI algorithms that I was going to be using in my project, which I will talk about more in a later video. But it's going to be fun, it's going to be a big one. And so, first one we're going to talk about is gradient descent. It's one of the most common commonly learned first algorithms you'll ever see, and it's pretty straightforward, pretty simple, and it's a form of linear regression. There's a video series. The link to the video series is going to be in the description because this guy explains it far better. He's a professor at Stanford. He explains it far better than I ever could, but he doesn't go into the code of it, and I thought it would be fun if we actually programmed one up in Python, our own gradient descent AI algorithm, our first little algorithm on this channel for artificial intelligence. So yeah, I'll put that in the description. It's a great video series. Doesn't take long to watch. It's under an hour, and he goes over a lot of the great formulas and what they mean. Okay, so I suggest watching that if you don't know a little bit about gradient descent. And so here is our gradient descent program. As you can see, it's not that long at all. So normally I would have coded it out with you guys, but it's so short. Like 30% of the program is just putting in stuff to the function, but it's really straightforward. Okay, if you've watched the gradient descent videos and you understand a bit about gradient descent, the first thing we need to do is calculate the cost, right? So I calculate the cost right here in this function. It's definitely short. Then I adjust the weights, and once I adjust the weights of my function, my linear function, then I need to go through another round and calculate the cost for that next round and such. And that's done in the main overall function in gradient descent. So it's just three programs. All gradient descent does is he separates out the data. There's going to be a lot of, because they're going to input tons of data and pairs and whatnot, and gradient descent's going to handle splitting that up into all the x inputs over here, all the y inputs over here, all the predicted values over here, and get it nice and spread out for us so we can access what we need to. And then it's going to run these two other functions, calc cost and adjust weights, over and over and over and over and over again for the however many times that we put in, which you can see down here. I even did 200,000, and it'll spit us out back the value. So let's get into it a little bit. So let's start with the gradient descent. Let's start down with the main. Let's look how they input data. So basically, let me open up a little bit of pain over here. Oh, that's lagging. But so they're going to input it in ordered pairs. Whoa. They're going to input it in ordered pairs, right? Like if I have, a graph, and I just have this line, and I have, this is 2, my x, and my y output is just, say, 1, and then over here I just have 4, and then, my y output is 3, something like that, right? It's going to take them in ordered pairs, just like points, just like how we're used to. That's supposed to be parentheses. So just x, should have got my mouse for this one. Y. You're going to put them into a list of all the ordered pairs, okay? As you see here. So 1, 4, and that's just this for a single variable function. When I was testing this, was playing with two variable functions. So it's 3x plus 2y equals z, a function with multiple weights. Or if you want to stick it in terms of x and y, you'd say 3x sub 1 plus 2x sub 2 equals y and such. So it's a multivariable function. This could be the cost of the house correlated with the square footage size and maybe the backyard space, two variables in there, or number of stories or number of bedrooms, something like that. So they input, so they're going to input the pairs, as a list themselves. So I have a list of all the ordered pairs, and the ordered pairs are going to be, first off, so they're going to be a list of their own. You see the first index is all of my x inputs, all right? So 1 and 4. And then the second index is just my y output, right? I'm only going to have one of these. I could have as many x inputs as I want, as long as they all have the same number of x inputs. But in this case, I was only playing with 2. If you want to work with it in 1, you would just put something 2, like that, right? But I'm not in this case. Yeah, I'm doing 2 variables, so I make it a list, right, of multiple. And the code will be able to detect whether it's 1 or not. Now, notice I'm working with a function that you may notice that all these are 1s, right? Ones, 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 ones. Well, am I not changing my input? Well, and I am. It's my function is y is equal to, mx. Man, I really should have busted out my mouse for this one. mx plus b, right? So my x input for that constant is just 1, right? Just the constant times 1, right? I'm not inputting any x value there. But when my program goes through and multiplies all the x inputs by their respective weights, which is like these m's out here, I just need to put a 1 in here so that I don't lose the constant, right? Because if I put in a 0, because I'm not putting in x inputs for the constant, it'll multiply by a 0 and you'll lose the constant. So I'm just putting in 1s as a placeholder just so it'll multiply my constant by 1, just so I know it's there in the outputs. There's probably different ways you could do that to get around it, but it's not too bad for me. And then you put in the weights, all right? So up above was your x and your y's. It was all your points, right? Down here are your weights, okay? These are what you think those m's are going to be. And as another kind of throwback to the constant, the first one is what you think your constant will be, by the way. So this will be multiplied by the 1, and this will be multiplied by the 4 and such, right? And obviously by this data, if we look at it, it looks like it's just 25 times 4 plus 10 times 1. That's what it looks like. Yeah, because 5 times 25 is 125. Yeah, so it looks like it's 25x plus 10. That looks like our function. So this is a terrible, terrible guess. It's not even going in the right direction, right? But that's okay. Gradient descent will figure that out. If you watch the videos, you'll show that the lines will eventually correct themselves every pass through, every couple pass-throughs. The function, when you call it, toolbar's in the way. Yeah, sure. The gradient descent function returns the cost and the weights. And this cost is a step-by-step playthrough on how bad your guesses were every run through. And this will spit out 200,000 different costs, right? Like different attempts. So I don't print that because obvious reasons, but I have it in there because if you want to analyze, you can write that to a text file so it doesn't like overload the serial monitor or whatever. So you can analyze how good your learning coefficient is, like you see in the videos. How good your initial guesses affect it. Like does like being really far off actually affect it a ton? And how it's useful for you to refine your algorithm and make it more efficient. You can see, oh, my costs aren't varying that much. I'm not that efficient. Or my costs are, boom, they're honing in like that. They only took 50,000 of the 200,000 attempts until I was there, right? And I could have stopped then. That's another way to see how many attempts I should need. So it's a way for you to review it. We don't need that. Weights is just the final estimate of these guys, and that it'll figure out. So let's dive into it. So I'm making an empty array for my costs because that's going to be useful when I'm predicting the new values. Because if we go over here, there's this function, the new weights. Every time you want to rejig your guess, like he said in the videos, is you take your old weight and you subtract the the derivative of the cost function, but it's useful. Yeah, you sum up all the cost and whatnot, and you're going to times it by your learning rate, and you're going to find the mean for that, and a whole bunch of other deals is going to affect that. And so, where was I? Yeah, so I have the cost here. I'm going to store those because I need those for mainly. Actually, I take that back. The cost isn't really needed in the functions because if you look, I misspoke there. My bad. So the cost, this isn't cost function. This is the derivative of the cost function. The cost function is just for our eyes, basically, to see how efficient we are. And let me pause that and go get my charger. All right, hey guys, back. So just wanted to reiterate. So I misspoke. We don't actually need, I looked at the functions. We actually don't need the cost for calculating anything. It's the derivatives of the cost, because that's the whole point of gradient descent. So we use the gradient or the derivatives to tell us where we need to be going, the rate of change of the cost, right? It explains that a lot in that playlist. If you watch that, I recommend it again. We're just mainly going to go over the code here. So, all right. So the cost is mainly for us, like I said, where we want to test the efficiency. So what I talked about earlier is when we separate out the inputs, so it makes it easier for us to use. I do this here. I do x inputs, and I take the first index of all these little, all these little pairs, right? And I put them in their own array, and I call it the x inputs, right? It's all my x values. For x, yeah, so I just go through every element in the training data, and I separate out the x inputs. Then I do the same for the y, because they're the second index, right? They're this 110 over here, right? So I separate them into their own. And then for how many steps they put in, I'm going to run through the calculating cost and adjusting the weights and such. And in this case, my testing data is 200,000. That's what I usually like to do. That's what I found. Well, I didn't do any feature scaling. That'll be for a future video, by the way, if you look at that. And I'll probably even use NumPy for the matrix way if you want to. So all we do is make our predicted value. So how we do that is we use this handy little function called numpy ... x weights for x and x inputs. So that could be complicated at first if you don't know how to use NumPy. So let me illustrate it out for you. Okay. So what we do is our functions like 3x per se plus 2 for our constant, right? Okay. So but these weights, they're stored in their own array, right? 3 and 1. And these x inputs, which are in themselves, oh, that's 2, by the way, 2. These x inputs are stored in their own array, okay? So maybe I'm putting in like just 5 for x right now, okay? And since this is a constant, we're just going to put 1, okay? Now, if I want to get my predicted value, well, I need to multiply this guy by that guy, and then I need to add it with this guy, multiply that with that guy. And that's basically just a dot product. If you've ever done vector calculus, what a dot product does is it just takes each respective element, so the first one and this one, the first one and this one, or the 0th index, the 0th index and the 0th index, multiplies them and then adds them to the next guy's multiplied, and so on. Right? So even if I had 10 variables in each one of these, it would multiply each respective guy and then add them all together. So that's what I'm doing here. It's a really handy function. So I just do numpy ... and I put in my x, which for x and x inputs. So I take all of my x inputs because they're each in their own respective list. Right? Each data point has their own list of x inputs. So I go through all of those little lists, and then I dot them together with their respective weights. And that'll get me my list of predicted values. Okay? All right, so that line may be a little hard to visualize at first, but if you go through it, and you're like, oh, I'm multiplying, I'm dotting the weights with their respective inputs, that'll give me a predicted value. And if I go through every point, I can predict what every little subsection of those, I can predict what each one of these little lists, right here and right here and right here, will give me. And that's important because that's how we calculate our cost. So once we plug those in, we plug in our predicted values, and we plug in the actual y input. So this is why it's becoming useful that we separated them out. So let's jump up to calc cost. Pretty small function. All we do is we get the length of the values, because we're calculating the average cost. So we're going to need to know the length, right? Because you divide by the length. And then all we do here is we're going to be using this formula right here, where you just take your predicted value, you subtract the actual value, you square that, and then you just take the mean with a 1/2 as well. Okay. The 1/2 is just useful because if I minimize the cost of one thing, even if I multiply in a 1/2, it's still the minimum. Like I didn't do anything different. It's still going to be the minimum weights it'll still have the same weights that'll minimize that cost. And that just takes away, when we derive it, if you've already done calculus, it takes away the 2. So that's why I put it there. It's just minimizing a function and then minimizing that same function with a constant out there. It's still going to be the same. We just put the 1/2 there so the 2 goes away. It's just easier for the calculations. And so all I do is I take the sum of all of the cost and I take the average. So let's see how I compute all the costs. So I go x minus y squared, right? So we get that predicted minus the actual squared, for x comma y in list zip predicted values. I put this, normally zip will do the job for you. I just put this because whenever I was testing and I try to print, sometimes zip returns zipped object at blah 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 and you need to use list. But in reality you only need the zip there when you're just running it. That was purely for testing purposes. And you'll see that, you may see that in a couple other places. What I do is I put the predicted values and the values and I put them in pairs, and then I just go through each pair, subtract, square, take them, add them all up, you see with the sum, and then I just return the average of it. Pretty straightforward. And then once I get those costs, I just append it to my list of costs, right? Okay. Not bad at all. Okay, so it'll give me my average cost for just in general. So this won't return you the cost of each individual weight, by the way. This will return you the overall average cost of all of your weight choices, right? So you would need to change this a little bit, maybe put like a for loop, and run through each respective weight if you wanted to get the average cost of picking a certain weight individually, not the overall guess. And that just depends on how deeply you want to go with your optimization. So let's go into weights, the final part. Okay, so all we do here is weights. The new weights is basically just, we update our weights by just adjusting them, calling adjust weights, put in our predicted values, our y inputs, our alpha, our weights. Wow, we put in a lot of stuff for this one. But as you can see, it's not terribly long, and let's go over it. So I make temp weights, and this is useful because when you're calculating what the new weight should be every time, if you update the weights right away, well, the calculations for the next couple weights will be thrown off, right? Because they use those values. So what I'm doing is I'm storing my calculated ones in a temporary array just for now, and then when I'm done calculating everything, then I overwrite with that list, so I don't get any false calculations. And then I don't even think I need maxes anymore. Yeah, I was using maxes for something. I don't need maxes anymore. I was testing some things earlier just to make sure it was all running pretty smooth. So there's a couple things in here that may have been left over from when I was trying to remove everything during the testing. Okay, so I don't need this num anymore. That was just for me tracking it. So this basically just could be for weight in weights. You don't need to do the enumerate and num. That was just for me to track what weights it's on, because I was going value by value to make sure all the calculations were correct. The differences. So I'm storing, because now we're working with this formula right here. So theta 1 minus, and these are the same formulas. This is just for your constant, but your weight minus your learning rate times the average of all the cost times the x input for that value. So say input 1 is 4, right? So I take the predicted value, I minus it, and I times it by my inputted value of 4. I'm just going to sum all of those guys over and over and over down all the inputs, and I'm going to average it, times it by my alpha, and subtract it from theta. Okay. And so, yeah, and that's what I do here. So I take all the differences, I do x minus y for xy and predicted values minus y input, so I just get all of my raw difference values. And then what I do is I go through every x input I do need num, right, I do need num. Aha, that's why. Because I'm going through each weight, and so when I'm timesing by my x input, that x sub I, right? Well, my x sub I is trapped inside of this array of all the weights, right? Of all the x inputs, right? So if I'm on weight number 0, I need to pull the 0th weight out, or the 0th input out of here to multiply in. So that's why I use num, because if I'm on, say, the first weight, or index 1 weight, I need to pull index 1 out of here. And that's what I use num for, okay? And num 2 is also used basically the same thing. Whatever difference I'm on, because I got to go through all the differences that I've calculated and multiply them by their respective x input, which I think I could have used num2 as well. I think I could have just went num. I'll look at that. Yeah, I think I could have just put num2, just like num. So I go through every difference, and then I multiply in their respective x inputs to match that value. Okay, and that's because we took a derivative. He explains that on the video. Then I just take the sum of all the differences divided by the length of how many differences there were, basically, because I'm taking the average, right? We're finding the average. And then my temp weights, I append my new guess for the weight by taking the current weight. I subtract alpha, and then I subtract alpha times my average derivative, right? So I take, basically all these different points on the derivative function, average them, multiply it by my learning rate, subtract it from alpha, I append it. And when I'm done, I return all my temp weights. That way I haven't overridden any of the weights when I'm in the middle of my calculations. And so then I just say weights is equal to those returned temp weights. And that's it. That's your gradient descent function. Now, I believe in the videos he talks about a good learning rate to choose. When I first ran this program, I just had one because I didn't know what to pick. I started programming before I watched the full video series, and it wasn't working for me. I was wondering why, and it's because he talks about in the video series your learning rates can get so high you'll bounce all around the function and you'll miss the minimum. I'll be bouncing all around this function trying to find the minimum, but I'm like going too aggressively everywhere. 0.001 works really great for me. 200,000 steps. It'll take a little bit to run, but it's been getting me almost spot on the values. I'll probably come back with a future video because it's definitely not optimized now. All right, but this is basic. Come back, probably do a little feature scaling, and then probably do one on the matrix multiplication. He talks about both those in this video series as well. It's a great video series. I highly suggest watching it because I assumed you did when running through this. But yeah, hope you have fun. And this is going to be an algorithm I'm going to use for linear regression in my big AI project I'm going to make a video series on. So hope you enjoyed it, learned something new, and have fun. See you later.